Okay, so the last talk this morning, Paul Balister, who's an expert in various different areas, including bootstrap percolation, which he's not talking about, various things in graph theory, including random geometric graphs and so on. His title doesn't tell us what he's going to talk about. I think it doesn't mean anything to me at all. If you do read the abstract, then you find it's something to do with random geometric graphs.
Okay, thank you, and thanks to the organisers for inviting me. Okay. Right, so basically the motivation for this subject is in random sensor networks. So the idea is that you have all of these sensors and you're trying to detect something, whatever that something is, and you scatter these, you have these sensors in some area. But often in practice, you can't necessarily position the sensors precisely where you want them to be. So there's some randomness in the positions. Quite often the sensors break, so perhaps you put more down and then some of them fail. And this sort of justifies the idea that in the sort of limit of ludicrously unreliable positioning and ludicrously unreliable sensors, but then putting way more of them in so as to compensate, you'll get in the limit a Poisson point process. So that justifies the model. We're going to imagine these sensors as a Poisson point process in the plane. So I'm sure everybody here knows what a Poisson point process is, but quickly go over it. The number of sensors in any fixed region is a Poisson variable with mean lambda times A, the area. Lambda is the intensity, and disjoint regions are independent of one another. And throughout this talk, just to reduce the number of variables by one, we can change all the length scales to assume that the intensity is in fact 1. And of course, the most important point is the probability of a Poisson variable being 0 is e to the minus the mean. So probability of an area being empty is exponential in the size of the area, the region. Okay, so now we come to the actual problem. What we're going to think about is a bunch of sensors along a long, thin strip. Okay, and these sensors have the property that they can detect an intruder who wanders a little bit too close to them. But they can only detect within a certain range. And we're going to assume, for simplicity, that all the ranges are exactly the same. Okay? And then the question is, if you've got this long strip, is it possible for an intruder to creep across from one side of the strip to the other? So it's like a border around a country or something. You imagine trying to stop the illegal immigrants getting across. Okay, and also we're going to make it hard for us by saying that the intruder actually knows or can see where the sensors are, so can plan his trip accordingly.
Thanks for George
Soros. An alternative description is that if you join two sensors, if their sensor regions overlap, then what you've got is a graph, a random geometric graph, and it's easy, basic topology of the plane is that there is a crossing path. The intruder can get across precisely when there isn't a graph path from left to right across the strip. Okay. So just to fix our notation, we're going to have a sensing radius of r over 2. Reason being that we want to join them with a distance r. I mean, it's just convention. Okay. Now, what happens if r is very, very small? Well, this is a well-studied model on the plane. This is the so-called Gilbert disk model. And it's known that if r is small enough, and numerically the best guess is for this r, this normalization is 1.2 for r, there is no percolation in the plane, which means all the graph components are small. So the graph basically becomes completely disconnected, so there'll be lots of crossing paths, and trying to stop the intruder will be hopeless. Okay, so we're typically going to want R to be noticeably larger than this. Now, what I said about the topology, it being equivalent to a path going from left to right, we can actually make this very, very precise. If I join sensors within R over 2 of a left-hand boundary and R over 2 of a right-hand boundary, introduce some fake vertices, and join them up like this, then in fact we have an exact equivalence between barrier coverage you can get across if and only if you don't have a path from S to T in this slightly expanded graph. Okay. And once again, since we're sometimes working on finite strips, I'm going to make the convention that we do allow sensors to go a little bit outside the rectangle on left and right. The reason for this is that if you strictly keep them within the rectangle, it's possible that the most likely sort of path across could be right at the ends, and that gives you some strange boundary effects that we're not actually very interested in. So to make it a little bit more homogeneous and to make the ends not special, we allow the sensors to go a little bit to the left or right, but they still have to be within the strip vertically. Okay, so what do we expect to happen? So we're going to think that R is large here, and you're going to step back a long way so you can't see the sensors. It's just a big scattering of points. And how can you, and R is very large, so everything is usually extremely well connected. So usually each sensor is connected to lots and lots of other sensors. What can go wrong? Okay, well, what typically goes wrong is if for some reason there is a large area that has no sensors in it. Okay, and so we're going to use this idea of excluded area. If you have an empty area, then things can go wrong. Okay, here's a bunch of different types of excluded area. Okay, on the first one, A, you could have an empty rectangle going across the strip of width R. And remember, these things were joined with their distance R, and they have sensor range R over 2, which means the intruder can sort of sneak down the middle. So this will cause a break in the barrier coverage. Okay. How many of these obstacles do we expect to have in the strip? Oh, by the way, the strip is of length L, long, and height H. Well, we expect, so since it's a Poisson process of intensity 1, one expects LH vertices to be in the entire strip, and the probability that each one is followed by an empty rectangle is just e to the minus the area of the rectangle, which is h times r. Multiply those two together, linearity of expectation, we expect about LH times e to the minus HR of these obstructions. Okay. Well, there are other things that can happen. So if you look at B, this area, perhaps there's just one isolated sensor that's sort of disconnected from everybody else. The chances of this happening are around about, if it's near the boundary, it's sort of e to the minus pi r squared over 2. If it occurs in the middle of the strip, it's more like e to the minus pi r squared, once again because of the excluded area. Okay. And then there's combinatorial factors in front. For the first one, it has to be around the bottom or the top, so that you don't get an extra factor of h. The second one, it can occur at any vertex. Okay. Of course, we don't really care about B and C because they didn't cause us any trouble. That doesn't allow an intruder to cross the strip. Only A here, out of A, B, and C, only A was the problem. However, if H is more than about pi r, so pi r over 2, you'll notice that C in particular will be a lot more common than A. So you get lots and lots of sort of, the graph becomes disconnected long before it matters. So you get lots of these tiny little components, but they're not a worry for us because they're not allowing an intruder to get across the strip. I've also drawn D and E, so A, D, and E are all examples where the barrier coverage has failed. But which one has the smallest area? Well, it's A. And one can prove that the smallest obstruction is just a simple rectangle. So because the probability goes as e to the minus the area, that means that D and E are considerably less likely than A. But they could still happen. Okay. The problem here is that there are lots of different things that can happen. You don't just have a rectangular strip across, a rectangular empty area. You could have a slightly tilted rectangular area or a slightly wobbly rectangular area, a rectangular area with bits in the middle. All sorts of strange things could happen. And because there are a lot more of these things, it could be that even though each one is individually less likely, they can sort of gang up on you and they can actually end up being the main obstruction. Okay. Now, for comparison, there are other areas in random graph theory and even random geometric graph theory where something goes wrong, but it's one clear identifiable thing that goes wrong which dominates. So, for example, both in the Erdős-Rényi graph and also in the corresponding Gilbert model, connectivity, what can go wrong with connectivity is an isolated vertex. Other things can go wrong, but they're much, much less likely. You're much less likely to see a component of size 2 than you are a component of size 1. If it's going to be disconnected, typically isolated vertices are the thing to look for. These are simple. One can estimate their probabilities. Okay, you have to do a lot of work to make sure that's correct, but at least you know sort of what the obstacle is. Whereas here there are lots of obstacles, and many of them, in particular, for example, the last one, E, could have area very, very close to A. So it might not be only very, very slightly less likely. And in fact, this is basically what happens. If H is not ridiculously large, so we have a proof for less than constant R squared, but in reality it's probably E to that. Most breaks are actually a sort of randomly wobbling rectangle as you go up. And the thing is, there's a lot more of these than there are just simple straight rectangles, and therefore, because there are a lot more of these, they can actually occur more frequently, even though each particular shape is less likely. Okay. And to put it in sort of physics terms, there's a trade-off between the entropy, which is, in some sense, the number of shapes, and the energy, which is the size of the empty area. So the energy, the bigger the area, the more difficult it is for these things to occur. But if you have a lot of them, they can gang up on you and still be more likely. Okay. If H is ridiculously large, for example, if it's exponentially in R squared, then it's not too difficult to see that eventually all sorts of crazy things are going to happen. You're going to, if I go back to this example, you'll get things like D happening, and you'll have little islands, and you'll have the thing looping round and doing all sorts of crazy things, because just simply there's so many more possible ways that it can fail. So, because strange things can happen, we have to be a little bit careful about what we mean by a break in the barrier coverage. So what is a break? So look at this horrible mess. We've got a bunch of small components scattered all over the place, and we've got a couple of these small components sort of sitting inside this sort of gap. But the intruder can go in lots of different ways. So lots of different topologically distinct paths that an intruder can take across this thing. So how many breaks are there? If you count all the topologically distinct ones, then perhaps the fundamental group's infinite. So perhaps there's infinitely many. Well, no, that's a silly way of counting it. Perhaps it's 2, perhaps it's 4. I don't know. Well, we don't want it to be anything other than 1. Right, sorry. The reason we want this to count as a single break is because at the end of the day, we're actually going to be estimating the probability that there's a break. And we like the breaks, therefore, to be independent of one another. If we consider this to be 2 breaks, those 2 breaks would be heavily dependent. The fact that one of those paths exists dramatically increases the probability that the second path will also exist because it's sharing a lot of the empty space. So what we want is to make this is a compound break. It's a nasty, complicated structure, but it is still, we just consider it to be a single break. Okay, so that gets back to the question: how do we define this formally? And the thing is not to do it in terms of breaks, but to do it in terms of the components. Okay. So we call a component good if it reaches both to the top and the bottom of the strip, more or less. How close? Well, it won't get to exactly the top, it won't get to exactly the bottom, but if it gets within root 3 over 2 times r of both the top and the bottom at some point, then no other component can sneak past it. So, and that actually turns out to be the useful definition. So you can't get a path sort of getting round this good component. I mean, so no other component can straddle it on both sides. I mean, you can have bits in the middle, and you can have bits to the left and right, but it can't sort of go round it. And then a break is just, so good components are then now ordered left to right, so well-defined ordering along the strip, and a break is just 2 neighboring components. It's the gap between 2 neighboring good components. Okay. Right, so let's start off with some results. The first ones are going to be rather easy. The definition of break makes sense. So what I've just defined to you, the barrier coverage does occur if and only if there are no breaks. So in other words, there aren't 2 good components. Okay. And breaks occur with a well-defined asymptotic density along the strip. This is just a godicity of the process. Okay. And I'm going to define the intensity as IHR. That's a function of both H and R. Of course, it was also a function of the density, but I set that, so the intensity of the process, I set that right at the beginning to be 1. So I don't have 3 variables, I only have 2. Okay. Slightly less easy results. For this, we're going to actually now have to assume R is big, and for this, R is at least 7 actually works. It doesn't have to be too enormous. The good components are usually wide, and the breaks are usually thin. And as a result, the breaks are few and far between. So you have big good component, small break, big good component, small break, and so on, along the strip. What do I mean by this? Well, you have to come up with a technical definition of what a width of a break is, and you have to come up with a technical definition of a width of a good component, and you can do this. And then you show that the expected width of a break is basically order H, unless H is ridiculously small, in which case there's almost no vertices, in which case the gaps get big again. And the expected width of a good component is at least exponential. By the way, these are these don't include R, but these are very, very weak statements. but we need them because we need the good components to be much wider than the brakes. But you know, one could prove in theory much stronger results. But even these are actually quite tricky to prove. And to give you an idea of why it's tricky to prove, if you're trying to show that a good component is typically wide, the standard thing to do is some sort of exploration process. You start exploring the space until you bump into a good component. This is the sort of blue area. So start from some place gamma where you've already, you know, decided what's happening, and then you explore to the right until you hit the first part of a good component. And a good component will have a path going across. Right. But the problem is, in doing so, the easiest way is to take a ball of an appropriate size and try and sort of see if it's constantly empty and sort of ram it to the right and see when it gets obstructed. So when you can think of the vertices of the good component as being the pegs that stop it going forward. And in order to find those pegs, you have to explore the blue area, which means you've actually explored some stuff to the right of the pegs that you've found. And now you've got to decide whether the more points on the right-hand side still form a good component, or is it the case that all the empty area I found now kills everything off? And that's geometrically horrible. So it's unpleasant, but it turns out that one can do this. Okay. Right. The next result is the reason we defined the brakes we did. We wanted them to be essentially independent of one another. The reason we want to do that is because they're few and far between and they're essentially independent of each other. This makes them essentially a Poisson distributed in any strip. So this uses the Stein-Chen method. The key feature is that the existence of one brake, because it's followed by a huge good component with very high probability, it means the next brake is essentially independent of it. I mean, it's so far away that it just doesn't involve any of the same area or any of the same vertices. Okay. So the conclusion, so the summary of this first part is, what have we got? We've got a definition of barrier coverage. We've got a definition of the failure of barrier coverage, is brakes. We've got a function of just the height and the radius such that the probability of the barrier coverage in an L by H strip, well, the number of brakes is essentially Poisson, it occurs with density IHR, so the probability that there aren't any brakes, so the probability that the whole thing is connected along the strip, or we have barrier coverage, is roughly e to the minus L times IHR. Okay. And we do need R to be a little bit on the large side for this result, but not that large. Okay. So, what's the next question? Next question is to figure out what the intensity is. So what this IHR is. What's the intensity of brakes? What are the brakes? What do they look like? How do we estimate the number of them? Okay. So going back to a naive idea of a brake looking like a rectangle, the probability a vertex is followed by an empty R by H rectangle is exactly e to the minus HR. As I said before, there are H vertices per unit length because it's Poisson process intensity 1 and the height of the strip is H. Thus, one would expect the intensity, if the vertical rectangular brakes were the only thing that mattered, the formula would be very simple. It's H e to the minus HR. So you just plug that into the previous formula and we think, you know, we're happy and everything's working. Well, okay, this is a lower bound because there are other types of brakes. Okay. So what is the result? The actual intensity of the brakes is a little bit more complicated. So there are essentially I've split it up into sort of three terms here. The e to the minus hr is what you expect at the beginning. That's the excluded area of a rectangle. And now we have some correction terms. This horrible mess in the front, and I haven't told you what this epsilon function is yet, gives you a combinatorial correction or an entropy correction to the result. Because this is counting things that are not quite rectangular, and I'll explain a little bit why it occurs in such a strange form in a moment. And this combinatorial factor sort of assumes that I've replaced the sensor regions by sort of parabolic regions, which you'll see as useful later on, but that's not quite right. And there are also some other problems with the approximation. So the green stuff is all the error terms. But the error terms are actually reasonably minor compared with everything else. Okay. All right.
7 is chosen so that 7 to the minus 5/3 is somehow
So
smaller.
what's
Why is, I mean, I'm trying to understand what the size of the error term.
Oh, okay. So the error term, if h is much smaller than r to the 5/3, then it's fine. It's multiplicative 1 plus little o1. Okay. I'm going to rephrase this in more simple functions in a moment, but this is sort of the best approximation. If h is a lot bigger than r to the 5/3, then obviously that error term starts to matter. But on the other hand, it's a lot smaller because r is reasonably big. It's actually much smaller than the hr. And it will even be smaller than the mess at the beginning. Okay. So what is the mess? So in general, how do you count brakes? Well, you count good components. It's one-to-one correspondence, except at the beginning and the end. Okay. How do you count good components? You count them by their last vertex. So the intensity of the IHR is basically just the intensity of vertices, which is h per unit length, times the probability that a uniformly chosen one of these vertices actually turns out to be the rightmost point of a good component. Okay. Now let's assume that h is reasonably small. So it's let's say much smaller than r. Then every component's good because there's in a very thin strip. There's no way a vertex can possibly be far away from either side, either the top or the bottom. And that's actually equal to. So let's look at this picture. So you're supposed to think of the height as being quite small. It's not being drawn very small here. But V and U and all the previous ones are typically, unless they're very far away, they're all joined up together. Okay. And what you need for this to be the end of the component is there to be nothing in the sort of pinkish area A. Because as long as everything stays away, at least distance r away from any vertex in the bit we've got up to so far, then that will be the start of a new component. Okay. So what I do is I'm going to approximate the disks by parabolic regions. These are parabolic regions pointing to the right here. And I'm going to this. So this gives me h times the expected value of e to the minus a. But I'm going to write A as basically HR, the rectangle, minus B. So I get H e to the minus HR times the expected value of e to the plus the area of B. So you think it's going to have to exclude a rectangle. It doesn't have to exclude quite that much because they can sort of sneak in a little bit from the right-hand side. And that takes off a little bit of area. So it's a little bit more likely. Okay. Right. And then, right, so now I do some messing around. I rotate the picture. I didn't actually need to do this, but I prefer to think of it like this. And then you scale by r to the minus third in one direction and r to the third in another direction. Now that sounds strange, but the reason is that if you do this, the intensity of the Poisson point process stays the same, okay, because the areas stay the same. And all the parabolas have now been put into a nice simple form. They're all just sort of, you know, x equals y squared. I made it y squared over 2 for convenience, but they're all of the same form. Okay. So what have we got? We've got a new model here where we take a vertical infinite strip, but with a floor. We put a Poisson point process of intensity 1 in it. Because we've conditioned on the last point, the rightmost point, that V point in the good component, there is one extra point at the base, which is uniformly positioned along the axis there. The width of the strip is now h times r to the minus 1/3, which is that horrible expression that occurred previously. And now I just define this epsilon function to be the expected value of e to that area, so the area below all the parabolas. Now I put an extra z factor in front. The reason for that is because it turns out to be convenient later. It makes the function look nicer, and that's really the only reason. So apart from a silly correction factor, this is basically just that last term, that expected value of this extra area that I can allow points to be in without messing up the break. Why have I done all of this? Well, it's simple. I've just reduced the number of variables from 2 to 1. So instead of having independent variables h and r, I've now only got one variable z, which is this h times r to the minus 1/3. Okay. Right. So what is this epsilon function? Well, epsilon z for small z is approximately z. That's easy to see. It's z times expectation of e to the area, and if everything's small, the area has to be small, so it's z times 1. A little bit more care and attention. You can do some horrible integrals over 1, 2, 3, 4, 5 points inside this thing. It turns out that you can actually do this exactly. If you reformulate it in the right way, it turns out to be some horrible things involving volumes of incredibly nasty polytopes in very high dimensions, which with a bit of work one can actually figure out what their volumes are exactly. So it's really just redoing all this integration and then expanding it out. And so you can actually get a Taylor series of this thing around the origin. That's as far as I managed to get. That last term, Mathematica basically pretty much broke down, but I managed to revive it sufficiently often to try and get it to get the volume of the appropriate polytope. Beyond that, it was hopeless. So this is a reasonable, and I put the 0 z to the 7 there because that term's missing, of course. The terms are easily all just z to the 1 mod 3, so there's a pattern, but no idea what the coefficients do. These are increasingly difficult to compute, and this will tell you absolutely nothing about what happens when z is large. In fact, going back to the definition, what happens if z is large? So z is the distance across. These are parabolas, so the height can go up to z squared. If you just have one point right at the end and nothing else, the parabola, so it's z squared times z, so z cubed area. This b could be of order z cubed. So e to the z cubed is a trivial upper bound. Okay. If that were the case, we'd be in trouble. And and also the other point is that if I just took the first term in that expansion, which is basically putting this area B to be empty, that gives you, and you plug it back into the formula, your intensity of breaks will just be your naive expectation if you're just looking at rectangular vacant areas. Ooh, okay. Well, the reason for this crazy definition is, I really don't want to go through the details of this, but this epsilon function is almost exactly multiplicative. That it turns out that you can split the region into two separate spaces and then do something on one side, do it on the other side, and represent it as some sort of crazy integral. So it ends up being very, very close to a constant times the product of epsilon on z1 and epsilon on z2. So it's an easy conclusion that it's actually e to the linear. It's not cubic in the exponent, it's just linear. And in fact, that little o1 term is in fact very rapidly decreasing. So it's actually an extremely good approximation. How good? This good. So numerical simulations tell me, I have no idea how to calculate alpha and beta rigorously, but the numerical simulations give this. I've subtracted it off the logarithm of the epsilon function, and look at the scale, that's minus 0.01. So basically, for z more than about 1, it's within about 1.5% of the correct value, and beyond about 3, you really, really can't tell the difference. So this is really actually a good approximation. Okay, extending things to larger h. This was everything here was with h sufficiently small that component equals good component. What happens is more complicated things. If you have enough room between the top and the bottom of the thing for odd things to happen, the area goes up. This makes things much, much less likely. One has to do a whole lot of area estimations and combinatorial estimations. But for h less than about CR squared, it doesn't make it. These horrible things don't actually matter, which is something I said earlier. For even larger h, we have to do we do a sort of doubling argument. So you cut your strip horizontally and say the probability of getting a break across the whole thing is the probability of getting across the first half, and then times the probability of getting across the second half. Well, no, because there's a horrible mess at the middle bit. But pages of geometry later, you can get at least some bounds. And then from this, you get your final result. So this is the way to think about it. If h is very much smaller than cube root of r, you have the naive with an error. If h is a lot bigger than the cube root of r, you get r to the third, e to the minus hr, which is what you think, some linear thing in hr to the minus 1/3, and then a very small error term. Okay. These are the simulations. This is just a simulation with that second thing, just with the linear approximation, with the estimates for alpha and beta before. And this is IA. This is essentially it's a log against h. And I only guaranteed that this was going to work for r at least 7. Okay. Those look sort of okay. This hasn't got up to large enough h, so that's unfair. But actually it works pretty well for 4, even well for 3, 2.5, 2, 1.75. Remember, the threshold for the Gilbert model is about 1.2, so at that point the thing becomes horizontal and everything breaks down. But if I actually put the real epsilon function in, it's even better. For 16, 8, 6, 4, you can't tell the difference. So it is actually a pretty good approximation, way below where I'd expect the thing to be reliable. I mean, all of these results should work for any r a constant away from the percolation threshold, but proving it would be impossible. We can't even prove that the percolation threshold is less than 1.25 anyway, so that's hopeless. And, okay, one of the things we can use these techniques for is we can use this to understand other issues relating to these sort of geometric graphs, like the sizes and shapes of the coverage holes. I mean, how circular are they? You know, we have this idea of, you know, if you have a gap which you just can't cover, is it circular? How does it deviate? How does the boundary look? All that sort of thing. Similarly, sizes and shapes of small components, number of vertices in small components, what shape do they look like, how big are they, how much area do they take up, and these sort of things. And I think I'll stop there.
Any questions, comments? I have one. So in the very large width, you said it becomes topologically complicated.
Yeah.
Is it still on a large scale going to look roughly like
Yes.
this?
So what happens is if you sort of have a certain amount of entropy per so the way, if you get a huge width, the way you get across it is essentially some path, okay? But the path is so long, you know, e to the constant r squared, that somewhere along the path it'll take a detour and do something silly. But for most of the path, it'll be almost rectangular. But as I said, it's just so long that other things will eventually happen at some point.
I guess my instinct is that the results like this, extremal results, are very sensitive to the details of the precise model you've gotten here. If one were to imagine this as some real-world problem, kind of a sorry, laughter from my right distracts me here. If hypothetically one were to imagine this as some real-world problem, and you want a more robust model, so kind of imagining that a sensor can detect something at distance r with some probability per unit time that decreases as a power law with r depending on the actual physics of the sensor.
Yes, that's a good point. The model is, of course, completely non-real life. However, I think some of the ideas still come through. So the idea of excluded area would translate to expected area that it can't detect, and so you'd use that instead. And the main contribution here is the amount of wiggling, and it's this sort of hr to the minus the third thing. And that's probably that probably doesn't depend too much on the model. Of course, all the constants do, and the proof does, and all the rest of it. But the basic idea of this sort of slightly wiggly path, and it's sort of entropy per unit distance along the break. I think that is a sort of more generic result.
Right, it would simplify. That would actually simplify a lot in mind. The model would be you can move at unit speed along a path, and so you want to sort of stay in the danger zone for a short time, and that would sort of encourage you to actually take straighter paths.
Yeah, but it's this sort of hr to the minus. I mean, it's the why the correction term is of this order, and yeah, I mean that's the sort of interesting thing.
I think we're all hungry, and the lunch break not very long until 1:30, so any more questions at lunch, but let's thank Paul and the other speakers.